Hi, everyone, and welcome to the Chapter 6 lecture on probability. Before we jump into the math, let's think about probability more broadly. Decide if you agree or disagree with any of these scenarios. That woman has been playing that slot machine without success for 2 hours, and she just quit. Let's play that one. It's got to pay off soon. My next door neighbor has had 3 boys, and she's pregnant again. This one's bound to be a girl. And lastly, in the first game of the night, my friend Henry won $100 playing Texas Hold'em because he was dealt 2 aces and there was another for the flop. He said, "I guess I should be big tonight. Cards are coming my way." Henry had a good strategy. So, do you agree with these scenarios? Do you disagree with any of them? We'll come back to this in a moment. When we're talking about probability, we are referring to a fraction or proportion of all possible outcomes. And this can be notated as a fraction in which number of possible successful outcomes, in other words, the outcome of interest, is in the numerator and the number of all possible outcomes is in the denominator. For instance, say you flip a coin. What is the chance that it lands on heads? Well, there are only 2 sides to a coin, right? Heads and tails. Heads is one outcome, and the number of outcomes available is 2. So this gives us 1 over 2, which is 0.5. You might interpret this as a 50% chance of the flip being heads. But what's important to note is that this probability stays the same no matter how many times you solve the equation. The chance of it being heads doesn't change with repetition. Let's take a look at a couple more examples. Say we're interested in the probability of buying a winning ticket for a lottery in which there are 1 million tickets sold and there are 800 possible winners. Taking that equation, we have 800 divided by 1 million, which gives us 0.0008, which can be interpreted as a 0.08% chance of winning the lottery. Or say we're interested in the probability of getting accepted into a class that has 140 places and 400 people have applied, and we're assuming that acceptance is a random draw. We would take that equation and have 140 divided by 400, which is 0.35, or a 35% chance of getting a seat. And again, you can solve this equation over and over, but you are still going to get the same numbers. The probability doesn't change with repetition. So why do we believe that the more we keep playing the lottery, the better our chances will be? Why do we think that because someone has had 3 boys, the next one will for sure be a girl? Well, people tend to experience gambler's fallacy, which is biased thinking in which an individual believes that a previous occurrence affects an ensuing occurrence, when in fact the two events are unrelated. Say you're living back in the caveman days and a predator, maybe a lion, was spotted nearby at some point. It hasn't been seen in a while, but thinking it's due to return any day helps you to stay vigilant and keep yourself safe. Or say there's a berry patch that hasn't produced food in a while, but you keep checking back because you think next time for sure. Again, this helps to keep you alive, even if it's not objective or scientific. Digging a little deeper, a normal distribution and a z-score can tell us a lot about probability. If you remember, a normal distribution has this bell-shaped curve and is symmetrical on both sides with the highest frequency in the middle. And z-scores, as discussed in Chapter 5, tell us the number of standard deviations of a specific data point. We can then take that shape and describe it by the proportions of area in each section. You'll notice that 34% of scores are within 1 standard deviation of the mean. 14% of scores are between 1 and 2 standard deviations, and so on. This rule applies for all normal distributions. Therefore, we refer to a normal curve as an exactly defined distribution. It's a very precise reference point. Because it is an exactly defined distribution, There is an exact relation between z-scores and the percent of cases above and below it. This means that if you know the z-score, you can determine the percent of cases above or below that score. For instance, say you have a z-score of 2.5. Using that precise distribution, you would be able to identify what percentage of people have scores above or below that number. This works the other way as well. If you know your relative position to others in a distribution, so the proportion above or below you, you can determine your z-score. For instance, say you're in the top 10% of a test. You can then determine what your z-score is. Let's do some practice with this. If someone has a z-score of 0, 50% of scores would be above this number, and 50% of scores would be below this number because the distribution is symmetrical. Likewise, we can flip this and say if a person has 50% of scores below them and 50% of scores above them, their z-score would be 0. But what if their z-score is -1? This would mean that 16% of scores would be below the score. We get that by adding the 14% and 2% to the left. And 84%, adding each percentage to the right, would be above the score. Here's a problem for you to try using that same addition as before. What is the percentage of people who fall between the mean and a z-score of +2? The answer will be shown in 5 seconds. The answer to this one is 48%, which we get by adding that 34 and 14%. So relating this back to probability, if you were to ask, what is the probability of a randomly selected score falling between this range, there would be a 48% chance of this happening. Again, the normal distribution and z-scores can tell you a lot about the likelihood of a specific score. You can also calculate percentages above and below a score when you have a raw score. You would just calculate the z-score first and then proceed as usual. I put the equations for calculating z-scores from populations and samples on the screen, but please refer to the Chapter 5 lecture if you need a refresher on this. And just as a reminder, to calculate z-scores, you do need a mean and standard deviation. So make sure you either have that information or have the ability to calculate it yourself if given a raw score. While you can calculate percentages or proportions by hand, it's kind of a pain to do, especially when the score is not a full standard deviation. So there's a table made essentially as a cheat sheet for you. This table is called a unit normal table, and it's posted on Canvas for you under the Start Here section in a folder titled Stats Tables. Because it is hard to see on the slide, here's a photo of that table but zoomed in so we can talk about what the table shows and how to interpret it. The unit normal table tells you areas, which we call proportions, under the curve for different z-scores. Starting at the top, you can see that column A lists z-score values from smallest to largest. The next column, column B, identifies the proportion of scores in the larger section, which we call the body. Before we take a look at the column, take a look at this image on the left. We have the z-score on the x-axis, and the body represents the majority of scores. For a positive score, this would be everything to the left of the score, and for a negative score, which is what that middle image is showing, the body is everything to the right of that score. The proportion is found in column B of the table as a decimal, but these are just the same percentages we talked about before. You can see that for the z-score 0, the proportion of the body is 0.5, which is 50%. And 0 is the mean when discussing z-scores. So 50% of scores are below this number and 50% of scores are above this number, just like we talked about in that previous example. Column C identifies the proportion in the smaller sections or tail of the graph. If the z-score is positive, that means the tail is to the right of the score. And if the z-score is negative, the tail is to the left of the score. And just like before, the proportions are listed in column C as a decimal. Lastly, we have column D, which identifies the proportion between the mean and the z-score. Taking a look at this image on the right, you can see that instead of telling us the proportion of everything above or below a score, it tells us only the proportion between the score and the mean, and that can be found in column D. So, putting it all together, say you have a z-score of 0.03, and you're asked to report each proportion. Finding the z-score in column A, just follow the numbers across. The numbers are not straight in this case because this document is scanned directly from the textbook, but you can see that the proportion in the body is 0.512, the proportion in the tail is 0.488, and the proportion between the mean and z is 0.012. And just as a side note, the table does not have negative z-scores listed, but because the distribution is symmetrical, a negative score has the same proportions as a positive score. This means that if you have a z-score of -2, the proportions would be the same as if it were positive. But proportions themselves are not negative, it's just the amount of area being taken up. So do not put a negative sign in front of the numbers. And as a last note, I do recommend printing out the table because it's easier to find and identify scores when you have a pencil or pen to mark them. It's not required, but it is something I find personally helpful. And that's all I have for you. If you have any questions, please let me know.